As people still start trickling in, my name is Andrew Hoffman. I'm a postdoc at Lamont. I'm one of the conveners for this session with my other conveners who can introduce themselves.
I'm Michael Field. I'm a second-year PhD student at the University of Florida.
Hi, my name is Natasha. I'm a third-year PhD student at the University of Wisconsin-Madison.
And this session is titled Observational and Modeling Gaps. So first, to start, we're going to have Jerry giving a presentation on the uncertain future of Antarctica, impacts of extreme weather events.
Hi everyone, I'm Jerry. I'm very happy to be here and present some of my research and also some of my work with my colleagues. So my talk today is about uncertain future of Antarctica, and then mainly focus on impacts of extreme weather event. So I'm going to bring everybody a little bit up to the air just to see more what happened on the surface. So I want to thank NSF for support my research, and also a lot of invaluable observations being collected during the YOP campaign season, which is a year of polar prediction. I will mention a little bit more in my talk. So, in the past few decades, we have more elevated atmospheric forcing over Antarctica in general, and that is being linked with our temperature changes. So over Antarctica Peninsula, we have a long time warming that is over 3 degrees Celsius in the past 60 years, and despite we have a very short period of cooling in the late 1990s. And also we have seen increase of the extreme high temperature and extensive surface melting in both strength and frequency. And over West Antarctica, that is mainly referring to the Marine Birdland region, we have more pronounced warming between the period of 1958 to 2012. And based on the climate projection we have at this moment, by the end of 2100, the temperature threshold of surface melting for a lot of ice shelf will be reached even under very moderate warming scenario. And also for the Northern Antarctica Peninsula and the coastal West Antarctica region, it's likely will have under stronger impact of the liquid precipitations. And that will trigger the rain on snow, a lot of like very important physical process, and will accelerate our ice loss. So one of the things that jumped in my mind when I moved to Scripps, start my postdoc, and then moved to a scientist, I found out that atmospheric rivers in polar region, although they happen in a very low frequency, it has strong impact over the ice surface. So here the figure I grabbed from Professor Helen and also Dr. Marty Ralph. That is one of all the components, a lot of information to unpack. I won't be able to go into details, but you can see how the ARs and a lot of like process can be triggered, like a chain effect. And the right panel B and panel C, that is the panel view and also the cross structure of the AR. So the take-home thing or the key message I want to pass here is for the atmospheric river, and they can bring not only heat, moisture, but also the things we overlook a little bit is about the low-level jet. The strong impact on the wind field, and the wind interact with local topo, it can trigger a lot of like regional factors and trigger the self-melting. So when we talk about AR, actually it can have two impacts, depend on the atmospheric forcing, atmospheric conditions we're looking at. It could add mass to the surface, snowfall, but also it can trigger the snow melting if we have very warmer conditions of the atmosphere. And that including rain on snow, and also including like cloud formation, we have radiative forcing on the surface. And also another thing I want to take a deeper look in today's talk is about the foam warming. And here is a map I label out based on the recent research, all the extreme weather events we've been noticed triggered by the AR events. And a few things I want to highlight, including the 2022 heat wave over East Antarctica being talked in previous talk already, that only one event dumped over 300 gigatons of snow on the surface. And I'm also in today's talk, I'm more focused on the surface melting events over the Antarctica Peninsula regions, and that is a compounding effect between both foam and AR. So before I jump into the detail scientific findings here, I want to show a tool being developed at the CW3E. I know everybody loves the QR code. So if you scan that, you can get to the website. That is a live tool forecast the AR activities over Antarctica along the coast. And we're still developing that, and hopefully we can not only have a live forecast tool, but also have archive data for everybody can use. So this polar AR scale, we are including not only the AR strength, but AR duration. So you will have a better ideas like how strong or how impactful the AR is, and link that with surface, ice surface changes. So back to the science. The 2022 February case over Antarctic Peninsula, we believe that is triggered by both foam and atmospheric river. And that is just a quick overview of this event. Because we have a low and blocking high pattern, there's a copper pattern here. We have very strong air Meridional IVT being transported from lower latitude to Antarctic Peninsula region. That brings tons of moistures and strong heat. And on the panel D, you can see how strong the interrogate water vapor, the IVT value is. And that event lasts for almost 3 days and triggered melting on the surface on both upwind side and the lee side. From slightly different mechanisms, upwind side is more liquid precipitation and the lee side is more linked to the foam warming. So, talking about foam warming, we kind of like no idea. The general things is about we have relatively warm and moist air come across the topography, orographically lifting, and on the lee side we have warmer and drier air. So for this case, we have see very strong foam signals. If you look at the 2 meter temperature, you can see it's clear the temperature difference on two sides. And also if we run across sections, you will see very strong mountain waves, which is in panel B, showing the black contour. That will trigger our sensible heat flux, basically the energy transfer between the upper warm foam flow and the colder air near the ice surface. So if we draw a box over Scar Inlet and try to calculate more quantitatively what changes, the 2 meter temperature raised for more than 5 degrees, and the 10 meter wind increased for more than 6 meters per second, and also the relative humidity dropped for 20%. That is all fit very classic foam, and that all happened in 24 hours. So then the question is like, the foam is not a new idea over the Antarctic Peninsula. Why the air important? Why air bring the changes to it? One of the things is like, if we look into two ideology like foam case scenario, one is called the shallow foam. That means we have relatively weak upcoming wind and a stable, relatively stable stratified atmosphere, like temperature inversion, warmer air on the top, colder air on the bottom. We'll have the low level blocking going on, and on the lee side is more likely we'll have hydraulic jump, which means the fast descending warm air can penetrate to the surface. That will trigger very strong turbulence near the surface, and that will have strong sensible heat flux. So, and also we likely have cloud-free zone along the foot of the mountain base. For this case scenario, we're more likely to have very intense but a limited area of self-melting. However, for the next scenario, we call the deep foam scenario, which is also happening in our 2022 cases. That means we'll have a stronger upcoming wind. If you remember, like AR also bring low-level jet, that also plays a role here. So that means on the lee side, we are more likely to have those mountain waves. And strong upwind precipitation release all the latent heat. So on the lee side, it's more likely we'll have wider border of melting and have stronger impact in general. So the perfect example is we look at two AR case triggered foam warming. One in 2015, that is a more typical shallow foam cases. You will see the cloud-free zone I just mentioned in real life. And in the panel D, you will see that is the case in 2022 February. We can see that is more shallow foam, a deep foam case. You will see the stripe of the cloud, and also that is stationary orographic gravity waves. So, without going into too much details, just on the past information is the AR actually matters to Antarctica with that the characteristic changes, either duration or directions or the strengths, we see different reactions in the local atmosphere. And if we want to get a conclusion here, it will be a very good way if we look at the surface energy balance component. Because if it's related to more cloud formation, liquid cloud, depend on the size, depend on the thickness, height, and the phases, it will show up in the radiative component on the surface, long wave or short wave. If it's more related to the mountain waves, we'll talk about here, related to the foam, then it will show in the sensible heat flux. And if it's like phase changes, like an upwind side, the liquid condensation, then we can use a trajectory model and we can check the latent heat release, which we did in research, but I don't have time to show the result. But I just want to say from a surface energy component point, and that data can be also graph on model and observation on the surface, ground observations, we can probably answer a lot of more regional factors will trigger those extreme events. So a little bit ongoing research and ideas I want to share with the community from more atmospheric scientist component. That is, we have the ongoing ideas. So one of the things I mentioned about the polar air scale we're talking about, and that I want to expand a little bit about the historic data set and the link with the impact on the surface. So here, just like two figures from my colleagues, and you can see, we will show, in an additive format, you will show visually how the AR being impacted certain regions, and hopefully it can bring in a way, not identify the AR, but also quantify the AR and their impacts over Antarctica ice surface. Another thing I noticed is about how the AR can trigger the cyclogenesis through like more positive feedback, like the AR-associated cyclogenesis. So that is not a new concept, especially if we talk about the lower latitude, like people here from Colorado probably heard about the 2019 bombing cyclone case, and that is triggered by the AR. That means when we have the AR bring all the moistures, we have latent heat release, and we power our potential vorticity in the lower troposphere, and that will enhance the cyclogenesis. So when we have stronger cyclone, stronger potential vorticity, stronger pressure gradient force, you will have the stronger moisture from lower latitude intrude more inland over Antarctica. That is also, we see a lot of a case not only have impact along the coast of Antarctica, but also more in the inland part. And here is just a quick example I run for a testing run in the polar wolf model. That is, not only you can see where I cut off the moisture, you will see a weaker AR, but if I highlight in the purple circle here, you will find that the mean sea level pressure, which is highlighted in the purple line here, the contour line, is much weaker if we cut off the moisture. There's a lot of testing we can still do, like we can change the SST, or we can change the thermodynamic process in the model. We will see more of these patterns to understand why AR is important for extreme weathers over Antarctica in general. And here's the last slide, almost the last slide of the Western Antarctica. We saw a positive trend of AR intrusion if you look at the Mariana IVT. And over Antarctica, Western Antarctica will be more complicated than AP region because the topography is more complicated. We have more mountain barriers instead of just one. So there's more things I want to do over this region, and I hope we can have not only model, but also observational data set. So I'm going to stop here because I'm running out of time. I'm trying to go over a lot of information, and I'm happy to discuss more in the talk. But I think the final take-home message of the list here, this is not only my idea, it's from a workshop actually held at Scripps between different scientists from oceanography, glaciologist, and also atmospheric scientists. So I highlight some points here is basically AR will add more uncertainty over Antarctic region in general, and we hope we can have better observations and better model data try to capture all those extreme events. And that is all my talk. Thanks so much.
Next, we have Helen Ockenden, who's going to present on inferring basal topography from surface observations.
Awesome. Hi, everyone. I'm Helen Ockenden. I'm a fourth-year PhD student at the University of Edinburgh, and I'm going to be talking today about inferring bed topography from surface topography. So hopefully by this point in the conference, everyone's kind of aware that bed topography is important because there's a lot of uncertainty in predictions of future sea level rise, and bed topography is one of the main contributors to this uncertainty. And for ice sheet models, we not only need the broad scale, sort of big picture topography, but we also need to know what's going on the small scales as well, because depending on what resolution bed topography you provide in models, you can get quite different results. And we heard from Duncan on Tuesday that Antarctica is actually the least well-surveyed crust in the inner solar system. So even though we have a fairly good idea on the broad scale, we actually, in a lot of places, we have no idea what's going on the small scales. So what do we do in areas where there are no observations of the bed? Well, in some areas where we do know what the bed topography looks like, we can see that there's this really startling resemblance between the surface topography and the bed topography. And there's actually a mathematical set of equations which describe this relationship. So if you have a given bed topography, what you would expect the surface topography and velocity to be. And what I've been working on is going the other way. So taking the surface topography and velocity fields and inverting those to predict what the bed topography should be. And I'm not going to go into all the details of the methodology today, but if you're interested, we've got papers looking at Thwaites Glacier and Pine Island Glacier that you can look for. So just to summarize some findings from those earlier papers, from synthetic tests, we know that this ice flow perturbation analysis methodology can resolve landforms as long as they're aligned at greater than 15 degrees to flow. So we can't resolve things that are aligned to flow, but we're not particularly concerned about that because features such as MSGL, erosional features like that, are actually too small a wavelength to see because we can only really see landforms with a wavelength greater than the ice thickness because they need to have an imprint in the surface above them. But we can see quite small amplitude features, so anything greater than about 10 meters amplitude. So that's quite cool. And we know from looking at areas with radar data on Pine Island and Thwaites that this methodology is quite good at detecting the locations of hills and troughs, but sometimes it struggles with the amplitudes because there's a trade-off between bed slipperiness, which is another really poorly constrained parameter, and the amplitude. But there's always, if there's a hill in the method, there's always a hill, no matter what slipperiness parameter you put in. So we're happy with their locations, even if not the sizes. And just to emphasize that we're providing mesoscale topography, not the broad scale topography, because we need to input a rough ice thickness. So here's just an example from Pine Island Glacier. So the ice flow perturbation analysis on the left, ice penetrating radar in the middle, and then bed machine on the right. So you can see that this hill feature is picked out really nicely by this method, and it's not present at all in bed machine. So I've been looking a little bit at Pine Island and Thwaites in the early part of my PhD, and now I've been moving on to applying this methodology across the whole of Antarctica. So I'm using the REMA surface elevation, its light velocity, and a 50-kilometer averaged ice thickness. So on a continental scale, it looks pretty much exactly the same as what we already know. And that's because this is just showing that broad scale topography. And just to emphasize that we don't really cover the coastal areas, and that's because the physics around the grounding line isn't really captured in the equations that we use. But if we zoom in and look at a much smaller scale, you can see that there's significantly more detail in the bed topography that we get from this method than from bed machine Antarctica. So this is a 50-kilometer grid, and here we have a 500-kilometer grid. So again, you can see in bed machine Antarctica, you can really see the locations of the radar survey lines, whereas because we have the surface data everywhere, we have the same resolution in our bed product everywhere. So just to highlight some interesting features that we found, in this part of East Antarctica, there's this really interesting subglacial channel feature, maybe. We don't really know what it is, but there's definitely an imprint of some kind of feature there. Here, we see a really strong linear trend across this region that might be some link to some kind of tectonic structures across there. We don't. Dunes in the ice surface. So we see this topography in the surface and we're like, oh, it must come from the bed. But actually, in this area, we know it's not. It's just coming from ice blowing across the surface. So it's not perfect, but it's still pretty cool. So just to summarize what we know, I haven't really had time to look across the whole of East Antarctica or West Antarctica yet. It's a massive area, loads of data. So if anyone has areas they're interested in, I'd be really interested to talk to you. But we've seen some cool new bed features, and we know that there's much more detail between the radar lines, but we also know there's some artifacts from surface data sets. So one thing I've been working on is trying to quantify like how much new topography that we're finding with this method. I settled for quite a kind of basic metric of just looking at how many maxima we have within a set area. So I'm defining these as anything that's got a 50-meter amplitude within a 5-kilometer radius, but obviously you could like play with those parameters. So I just ran this across the whole of Antarctica on about 4,000 50 by 50 kilometer grids. So yeah, what you're seeing is the redder the area is, the more of these local maxima, like bumpy features you see. So for the ice flow perturbation analysis method, we see a pattern that's quite strongly linked to ice velocities. So we're seeing much more bumpiness around the edge of Antarctica than we are in the center. And that's just because the faster the ice is flowing over the bed, the better this transfer of features from the bed topography to the ice surfaces. So in interior areas where the ice is flowing much slower, it takes much longer to get these features from the bed to the surface, so you don't see as much transfer. Whereas if we look at bed machine Antarctica bed topography, the pattern that we see in this bumpiness is much more influenced by where we know we've got really good detailed radar surveys. So you can see like Lake Vostok and the Gamatsev Mountains being picked out there as like more bumpy areas. So we can see that that's really influenced by the location of radar surveys. Whereas our method, obviously, we're not putting in that radar survey data. So we've got much more universally similar coverage. And if we take the difference between the bumpiness of this ice flow perturbation analysis and bed machine, we can, so if it's more red, that means there's more bumps in the ice flow perturbation analysis. If it's more blue, there's more bumps in bed machine. Then we can see that pretty much universally across Antarctica, with the exception of a few places, we're seeing more bumpiness in this new method. So we're picking out hills and valley features that we didn't know were there before. And if we sum this all up, the total number of features that we've added is about 40,000 new, like, lumpy, bumpy features, which is pretty cool. So future work, I want to spend a bit more time looking across the whole of Antarctica. It's a big job, to find interesting features, cool things that might be interesting to look at more in the future. And also, because we only use a very rough, averaged 50-kilometer ice thickness across the whole of Antarctica, there are areas where we obviously do have radar data, so I want to look into ways of incorporating the ice flow perturbation analysis with the existing radar data to make a product that's more useful for modelers, because there are some places where this doesn't quite match up, and obviously if we know what is actually there, then we should be using that in models instead of this. Cool. Thank you very much. And just to say, I'm finishing my PhD in January, so if anyone is looking for postdocs, come talk to me.
Yeah. Thank you, Helen. All right, next we have Philipp, who's going to be talking about ISAT-2 measurements of superglacial lake activity.
Yeah, thank you. I am a PhD student at the Scripps Polar Center in San Diego, and let's talk about surface melt lakes. So, this is what it looks like when the ISAT-2 satellite passes over a melt lake. ISAT-2 is a laser altimeter that uses green light to measure the elevation of the Earth. But over melt lakes, that green light is able to pass through the water, and so you get a surface return and a lake bed return, and you get this nice data that's a transect that gives you the depth of the lake. So if you've been to prior WAIS meetings, you probably know that I've been spending a couple of years now trying to find all these lakes, and I'm now happy to report that I did find them all, or at least the vast majority. So just to prove to you that this is not a bunch of red dots on the map, I have a very busy plot with a lot of examples of ISAT-2 melt lake depths. So to get there, I had to crunch 133 terabytes of point cloud data, which amounted to 715 billion geolocated photons. And only 0.07% of that data was melt lakes. Now, you might ask yourself, why would this guy spend the better part of his late 20s just looking through this vast amount of data? Or, more simply put, who cares? So if you've listened to Stacy's and Johnny's talks, you know why melt lakes in Greenland are really important. So I'll focus on Antarctica. We see that here, most of the melt lakes are around the floating ice shelves. And the floating ice shelves actually act kind of like a plug that keeps more grounded ice from flowing into the ocean. We call that buttressing, because just like the buttress on that building keeps the walls of the building from collapsing outwards, the ice shelves push back onto the grounded ice and keep the ice sheet from collapsing into the ocean. Now, if we have melt on ice shelves, that's kind of a bad thing to see, because when we have water, it can flow into crevasses and it can pry them open. And if we have lakes, there's enough water to sustain that fracture propagation, and that can lead to ice shelf collapse. And this has happened on the Lassen B ice shelf in Antarctica, where now the buttress is gone and the grounded ice is flowing into the ocean faster, which is bad news. It means sea level rise. We already see coastal flooding now, so I think you all should care, but especially if you have beachfront property. So we really need to keep a close eye on melt lakes, and to better understand these processes in which melt lakes ultimately lead to sea level rise, there's a bunch of questions we need to answer so that we can properly incorporate them into ice sheet-wide or even global climate models. And one very simple question to start with is, how much water is there? And that's actually the observational gap that I'm trying to fill here. Because the difficulty here is we don't know how deep the water is usually, and in the past, we've kind of used, like, looking at satellite images and using how deep or like how dark of a shade of blue the lakes is as a physics-educated guess of how deep they are. But of course that now has changed because we have ISAT-2 and its really unique capability of looking through water. So how does one find all these lakes and all this data? I developed an algorithm for detecting melt lakes in that data, the fluid algorithm for flat lake and underlying ice detection. And that takes a photon cloud in and it chops it up into segments, looks at whether there's a flat enough surface for it to be surface meltwater. And once we have those segments, then we can get a photon density out of this, and that helps us trying to see if there's a signal below that flat surface. And now we have to start taking all those segments that are potentially lakes and merge them together into one lake if they fit. So here, this is like an easy agglomerative clustering algorithm. It first finds 3 lakes, but then there's a last check on the surface elevation, and that figures out in this segment we just have 1 lake. And that would be the output of 1 detected lake. So now we have to figure out how deep they are. For that, I have another algorithm, the SURF algorithm for surface removal and robust fit. And this takes into, as input, 1 detected lake. It removes some of the sensor artifacts, again gets the photon density, fits the flat surface, removes that photon data, and then fits a smooth line, tries to figure out how good the fit is in that actually being a bottom return, and from that we can fit a line to where we have that return and determine the depth. And that is the output just of 1 lake of this algorithm. So to figure out where the lakes are, we need to know where to look. I used the IMBY basins, including the ice shelves in Antarctica, and I cut them off at an elevation threshold beyond which we don't expect to see surface melt. And that resulted in a list of 50,000 very large granules. And in the absence of massive funding for cloud computing credits, I used the OSG's Open Science pool for distributed high throughput computing. And this is just a general figure of how I implemented this. The main point here is for every single granule, there is 1 computer somewhere in the world that runs my algorithm on that granule and sends the data back to me. And once all these computers have sent their results back to me, I end up with this big data set of melt lake depths. So now that we know how this works, let's take a look at some examples. The deepest lake found was 27 meters deep in Greenland. The longest lake, over 7 kilometers long in Antarctica, and just happens to be right next to that doe line that Chase presented on. So that's kind of cool. The furthest south lake we found as far south as 85.3 south on Mercer Ice Stream, something that not many people have looked at there. And sometimes if we look at the data, there is ice cover on the lake. So in this case, we just only take the bottom signal where we can look through the water and where there's no ice cover. And sometimes this returns something that looks kind of weird. But I hope you have looked at Nicholas's and Rogers' posters, because there is a hypothesis that ice shelves flex up on the side and they have a foot that's submerged under the water whose buoyancy makes the ice shelf flex up. And that's actually exactly what that data is. So I can now with confidence say the ice shelf does indeed have a foot. It was just classified as a lake in my data. So I didn't come here to talk about feet, so back to all the lakes. We want to see some statistics because now we have all this data. So just looking at the broad lake depth distribution, We can see in red here the Greenland ice sheet has a heavier tail towards deeper lakes, and we expect that because lakes form where bedrock topography forms troughs, and that just forms deeper lakes rather than on the flat ice shelves in Antarctica. Now, splitting this up by region, the 90th percentile of maximum lake depth here, we can see the deepest lakes are in northwest Greenland, actually. Antarctica has much less deep lakes, and it's a little bit more uniform. But it has to be mentioned here, there is evidence of really deep melt lakes that are often ice-covered on ice shelves up to more than 100 meters deep. So there are deep lakes in Antarctica, too. If we look at like the timing of the melt season or when we see those lakes, those are centered around the middle of the summer for both ice sheets, and kind of a little bit towards the later side because ICET2 can see through kind of transparent thin layers of congelation ice. So this might be shifted a little bit later. If we look at every single melt season, we see that melt water availability can be driven by really big melt events. And interestingly enough, on the Greenland ice sheet, we see that the melt season, at least for the last 4 years, has moved progressively later. For 2003, we don't have all the data yet, but we just had a massive melt event very late in the season, so I expect that trend to continue. And we can also finally look at the melt lake elevations. It's no big surprise here in Antarctica, they're mostly below 150 meters because all the melt lakes are very close or on the ice shelves. In Greenland, we see melt lakes anywhere from like sea level to almost 2,000 meters of elevation. And we can, again, look at this a little bit more detailed. In Antarctica, mostly the melt lakes are fairly low elevation, but in Greenland, we see a really nice north to south gradient, where as we move further south, we see melt lakes at higher elevations because the percolation zone will be at higher elevations where it's warmer. And that's all the stats I have. For my next steps, I will publish all this ICET2 melt lake depth data and this inventory, so keep an eye out for a paper soon. And then I would like to use this data in conjunction with Sentinel-2 data to tune existing models that get meltwater volumes based on imagery, or even train my own statistical learning models based on that labeled data set that I now have. Yeah, I'm thankful for funding from NASA, thankful to the WAIS conference organizers for funding to be able to be here, and thankful for the OSG for providing all these huge computational resources, and of course also to my advisor, Helen Fricker. Yeah, so if you would like to talk to me, find me here while I'm still, or feel time. Summer, so if you are looking for a postdoc and like what you saw, then don't be shy. Thank you.
Great talk, Philipp. We'll actually have all of our speakers now come down to the front to answer questions. And again, a reminder that the last 3 presenters were all students, and so if you can evaluate them, please do.
We don't need my face up there the entire time, do we?
Good? Okay. This is a question for Helen and for Philipp. So really cool things that you're using to look at all of these like lakes and subglacial features. I'm curious about your thoughts on this being like a snapshot of Antarctica during this time, and like, so if bed forms are continuously aggrading under the ice sheet versus the lakes are changing, or if you have large changes in the superglacial hydrology, do you think that you would have to redo all of this analysis, and how often you would like to, if you had any resources to be able to get different snapshots? Does that make sense? Of like the lakes that you see now versus like how far in the future you would like to reanalyze that based on how quickly you think they're changing, and same with the subglacial topography and with like bed forms that are constantly being created near the margins.
Yeah, I think my answer is pretty much everyone else's answer. I would like to look at all the lakes all the time, everywhere. I mean, for that to be feasible, right now we only have ISAT-2, and that's the only thing that can look through water. Of course, it would be great to have an ISAT-2 that has more laser beams or multiple ISAT-2s, and then it should also have a camera on it. That would be something that would actually be fantastic if we could have something that images and takes laser altimetry measurements on the same spacecraft, because one of the issues is that we need to match up this data from different satellite missions. And then, of course, mission continuity would be great into the future. We need time series that don't just last for a few years. So I think that's a couple of the aspects. But yeah, I mean, more lasers, more science.
Yeah, I guess we know from observations from like Rutherford Ice Stream and other places that there is actively changing erosion, forming new bed forms under the Antarctic ice sheet. I guess from my perspective, I'm mostly looking at things that are a little bit bigger than the landforms that we know are forming. So potentially it would take a lot longer also for changes in the bed to reach the ice surface as well. In the model, we assume that the ice sheet is in kind of a steady state, which we know is not a great assumption for a lot of West Antarctica, but it's kind of the best we can do right now. But yeah, I think what would be super interesting is to look at like different timestamps of the ice surface and the velocity, and see whether that does make a difference in the bed forms that we see or not. That's not something I've done yet, but something that would be really cool to do in the future.
So I had a question for Philipp. So about a decade ago, we put a lot of effort into looking at subglacial Lake Willans. I wondered, just from your survey, how does that look? Is it typical? Is it atypical? You know, do we pick a good place to have a look, or maybe not?
You're talking about subglacial Lake Willans? I don't see any surface melt around there, so no. Yeah, we don't see any interactions between surface melt there, because there's at least no surface melt like water pooling there. But I might take that up to actually answer Peter's questions from earlier, because I said I could. Peter was, and this is related, he was asking whether you see melt lakes draining above the grounding line, and whether you could see like a Greenlandification of the Antarctic ice sheet in response to Tyler's talk, and whether you could see more subglacial discharge from meltwater input from the surface. And my answer is that we've seen this a few times. We've actually seen some surface melt lakes drain above the grounding line at the Amory ice shelf. It doesn't seem to happen very often now, but it would be very reasonable to believe that with more surface melt, that will happen more often.
Okay. I have a question for Jerry, though I would also, invite any of the other speakers to respond if you have thoughts on this as well. I really liked your talk, and I have a question when it comes to future climate in Antarctica. We've seen, and you highlighted in your figure that showed a map of Antarctica with selected extreme Antarctic atmospheric rivers, that individual events can have really big impacts, and individual events can also trigger large changes in a very short amount of time. But we're also seeing these longer term trends and changes in climate that are leading to these maybe more gradual changes or preconditioning of the firn or ice sheet for these more drastic events. So when you think about future climate, what do you think is the most important, or do you have a thought on what's more important, these triggering really extreme events or the gradual change or combination of both?
Yeah, I definitely believe it's a combination of both. Of course, the extreme events will be more exciting, and the frequency of that in the future will be interesting to see. Another thing is for a lot of positive feedback in those extreme events is not well understood, at least from a scientist point. So for example, polar wolf is a non-hydrostatic model I'm using, but it doesn't have very good land-surface interaction description. That is also why I'm here to understand more. Like in polar wolf, we don't have description of dynamic change of air albedo. So basically all the surface meltings being captured in the satellite actually is not incorporated very well in the model. That means that our near surface temperature now simulation and also projecting the future is not that correct. So there's a lot of things we can do to improve the near surface condition and try to understand why we have those melting on the surface. And back to your question, yes, the long-term or gradual change, that also matters, but also it depends on if we understand all the physical mechanism behind that better. So thanks.
So talking about ice shelf collapse, I think, yeah, it's a combination of both. You need a long-term trend of firn saturation to be able for meltwater to pool on ice shelves, and only then you're able to, well, crack it up. But you then usually need an extreme event in terms of an extreme melt event that actually triggers the thing. So we've seen that with Larsen B. There was a huge melt event, and then hydrofracture happened. So I think it's the long-term change that preconditions the ice shelves, but you still do need those extreme events. And if the extreme events get stronger, you'll get that trigger earlier. If you get more preconditioning, you'll also get, you need less big extreme events for it to happen. So it really is a combination of both.
My question is also for Jerry, and it's about the phone winds. And when we had a talk on Tuesday about atmospheric rivers, the speaker made the analogy to the west coast of the US. And so my question about your talk and the atmospheric rivers and the phone winds is, can you use the west coast of North America as an analog also? Because there's phone winds or Chinook winds, and as we know from the news, lots of atmospheric rivers. So does that serve as an analog for us?
Yeah, so you're talking about like a more like a merit, how to identify the foam and how the impact they are. So I believe over Antarctica, things can be slightly different because we're looking at the ice surface. So when the foam wind actually hit the surface, if we have the melting going on, we also have sublimation. So it's kind of a complicated situation. That is why for a lot of, especially for relative humidity, when I check on the foam, it won't be idealized like foam like we see in US. We have very dry, warm air on the lee side because we have the sublimation going on. Sometimes we have multiple source of the moisture reaching the lee side, like Eastern Ross Ice Shelf, for example. The 2016 melted case actually is combined air and the foam, but we have the moisture directly from Ross Sea region, complicated figure. So I would say we have to tweak or change our standard or the criteria a little bit to fit different cases, but in general, we should have at least see the temperature jump and also wind speed jump in those foam-related air cases. But we should have like a quantified way to do, like, for example, 24 hours of temperature changes or like the wind speed changes can identify that pretty well. I believe there are several research doing like even machine learning to identify the phone cases, and also over US, very similar story, but a slightly different criteria. Yeah, thanks.
My question is for Helen, actually. So you kind of touched on this, but the transfer from like a bed bump to the surface depends on how slippery the bed is, right? And so in addition to basal topography, we also know not a whole lot for models about basal slip, which could be important with changing extreme events or meltwater straining. So I'm curious if you could use similar methods to what you're using. Let's say if you know the bed topography from radar, could you actually kind of use your method to invert for basal slip instead of inverting for the basal topography?
Yeah, so actually that's what most ice sheet models do. They assume a fixed bed topography. They invert the surface properties for slipperiness, which is this like nebulous property that encompasses hydrology and sediment properties and like all sorts of other things that's just kind of wound up into this number that you slide into the model. So they, assume a fixed topography and then put these parameters in to get slipperiness and then model forwards from that. So yeah, in this inversion, we assume like an average slipperiness everywhere, but we do then also model like variations in slipperiness. But because we know so little about slipperiness, generally we're like really uncertain in that parameter. So on Thwaites and Pine Island, where we do have these high resolution radar grids of the bed topography, we kind of use those areas where we know what the topography is to constrain this slipperiness parameter that we put into the model. But as I said, because we know so little about slipperiness, we kind of would like to sell our product more as like we're showing the locations of these features, but not necessarily their amplitudes perfectly because of this trade-off between slipperiness.
Yeah, thanks everybody. This one for Philipp, but maybe can go broader than that. Philipp, you mentioned, this amazing inventory you have, but you've kind of focused a lot of them on the ice shelves. But it looked like there was a lot of red dots along the Transantarctics, and just a comment to or a question to ask if you've considered further classifying those, because obviously there's huge albedo differences between the rock exposures, and that can lead to favorable conditions for pooling water, and I think it could be quite linked with some of the atmospheric interactions with rocks as well. So yeah, just thanks.
Yeah, just a quick comment on that. We do see some melt above the ice shelves. This is just the motivation right now is mostly like ice shelf collapse, but it is, especially thinking about Tyler's work, for example, it is interesting to see what's happening above the grounding line, and a few lakes that I found along the Filchner ice shelf, for example, were just melt lakes that pooled right next to a rock that stuck out. The transatlantic mountains are there, and there's no other melt lakes. So we do see that, and there is a few lakes that were still misclassified, and I just got this data back a week and a half ago, so I need to figure this out a little bit, but there were a few lakes, what do you call those, ice marginal lakes that were misclassified. I did find a bathymetry profile of one lake in the dry valleys, so there is a few lakes that don't quite match up the classification, and because I primarily want to use this data set in conjunction with imagery to then train models that can actually get evolved, and we can just at least not use those for the analysis we want to use it for.
I have a quick question for Philipp as well. So in some cases, the ice bottom return looks a bit noisy. So have you thought about using Gaussian process regression or some other method to do some uncertainty quantification?
Yes. Not all the data is perfect, that's true. I definitely showed off some of the better examples too. Yeah, that is one of the things I might also think about, and I will also publish this data set alongside all of the photons that were used to find this. So I very much, once I get the chance to publish this, would also invite other people to look at that, because now at least we know where all the lakes are, and that makes it much easier for people to improve the estimates. And I have a rough uncertainty estimate by just fitting this non-parametric regression. You can look kind of at the standard deviation of the spread. So it's not an uncertainty so much as it is a spread of the photons, but that usually is fairly related. So I know width of the fit, and that's also what I use to find the confidence in the fit partially.
All right, I'm gonna ask a question. Gotti, we've talked a lot about the atmosphere in this session, but the ocean we know is also really, really important for driving a lot of the change we observe at Thwaites, especially. And I'm wondering if you've given this great example of how melt can intrude inland of kind of grounded areas or areas that are often used in model domains as being grounded. And I want to know more about kind of how you define or think about kind of extending your research in the future. Like what are you, and especially in terms of maybe some of these other parameters or related work with that we've heard over the last couple sessions from discharge, either from surface that percolates down or from subglacial lake activity.
So basically what I would like to do eventually would be to actually give a parameterization of the melt in the grounding zone. This parameterization would be simply using some variables like thermal forcing or the grounding zone migration width. It can be the discharge flux of subglacial water and stuff like that, which climate models can use, and they can actually run their models and give projections. That's where we want to go. For Petermann Glacier, we did it already. There is a parameterization which we proposed for the Petermann Glacier, but for Thwaites, it's still going on. Interestingly, the parameterization for Petermann is not going to work for Thwaites because the variables were really two variables, and we have more, I think, the retrograde, which is not the case in Petermann. So yeah, I think I answered your question.
Yeah, thank you.
Yeah.
Yeah, I've got a more general question for Philipp. Obviously, you're focused on surface lakes and melting, but what's your feeling about what the ultimate nemesis of most ice shelves will be? Will it be the surface melt or will it be the basal melt?
That's a good question, and I think my diplomatic answer is both. Because yeah, the more ice shelves thin, the less able they are to withstand large melt lakes, and the easier it is to break them up. So on the Amory, where like the closer to the grounding line on the Amory, we've seen these massive, like my example that I showed, these massive melt lakes that drained. But this is such a buttressed area that nothing much happens, and the ice thickness is really thick there. Once you thin that and you get less buttressing, I think it gets much easier for surface melt to damage the ice shelves and ultimately lead to their collapse. So I think they go hand in hand.
Yeah, I think that's good.
Maybe Gotti can also respond to that too. I think there's, I think as part of the basal process. Yes.
I also think that both processes play a role there. At the end of the day, when you have surface melt, it will eventually percolate to the bottom, and it will actually make the ice flow faster. And also, that implies that the grounded ice, which was previously grounded, is going to be exposed to the ocean, and you have basal melting at the base. So I think both of them actually would play a role.
Yeah, so sessions like this scare me because it's these really hard to see processes and we have no context, right? Like, have we been having these intrusions forever and we're just only able to observe them now? And I have the same issue with atmospheric rivers. Like, what's our hope for going back in time to understand the context of some of these processes?
Anyone want to take that one? You should be scared, Matt. I don't think I have a good answer for that. At least for surface melt, I don't see a good way of looking back in time, and maybe someone can correct me for that, but yes.
Yeah, I mean, ice cores, of course, is going to be my answer. I mean, we can go places adjacent to ice shelves to, capture the last few centuries or last few millennia of activity, and if we are really careful and use all of these great satellite resources with the overlap period in the modern reanalysis era to find if there are any chemical proxies in the ice core that vary in a way that is similar to ice shelf processes, the atmospheric processes that lead to lake formation, ocean processes that lead to intrusions under ice shelves. I think there's a huge amount of work that we could do there. And so again, I'm excited that we can hopefully get one of the first ice cores right, 200 kilometers west of Thwaites this season, and we'll see what we can do with that. I mean, there are also other ice cores up in the upper Thwaites Glacier Basin, and just thinking of that region where you can start to think about doing this.
Thanks, Peter, for making Matt less scared. Anyone else? Yeah.
So yeah, I just personally want to know about the history too, like what AR looks like in the past, because we don't have that. We only trust the data after 1979, which I hope we can extend a little bit more. But also it's like even in the existing period, we know of the past 60 years, when actually we do the station reconstruction data set with M5, with the reanalysis we have, it already shows some uncertainties or difference or inconsistent between data sets. So I think we need to be very careful when interpolate even the weather data we believe is trustworthy. Not trying to make the question more complicated here, but yes, I do believe the ice core data can provide us some history about what happened in the past. Yeah, thanks.
Just to add to the paleo perspective, maybe not paleo, but Robin Bell wrote a really nice paper on surface melt and looked at the Nansen, the really amazing kind of waterfall feature, but she documented some of the original observations from Priestley et al. In the turn of the century, 20th century. So I think there's quite a lot of historical information in some of those observations, as well as the amazing aerial photos that have been taken since the 50s. Can also be another recorder of that and connect with the satellite imagery. And then just a plug for the PRR. We have a really amazing media archive that has ground photos from places all around the ice that can serve as another kind of useful tool for these archives back at least a few decades.
Yeah.
So
Thank you.
We know that melt lake drainages have happened, and people have documented doe lines in the 1930s at least. I'm sure they have happened way before that, but there is historical imagery, so thank you.
Yeah, can't let Peter get away with mentioning ice cores without sticking up for coastal marine cores as well. And there are some people looking at very promising proxies for meltwater in marine cores, and Julia and her students can date these things to a few decades, so we could it's not quite there yet, I think, but we probably will be able to get meltwater records from coastal cores. And in terms of historical records, which Jamie was just talking about, I mean, one that came to my attention really is there's amazing photos from an expedition down into the Bellingshausen Sea 125 years ago where they were frozen in. There's all these photos of them actually cutting the sea ice with saws in an area where the last few years there's been absolutely no sea ice at all. And this is really sobering to think of how much change there's been in 125 years in that area.
All right, thank you. I think we're going to have to wrap it up at that. We have some announcements, I think, from NSF and Matt, so, and then we'll have a small break.
Give them applause again.